Hello students. In today's video, I am going to discuss the stereochemical aspects of nucleophilic substitution reactions. So, without wasting any time, let's begin the video and explore stereochemical aspects of nucleophilic substitution reactions. Stereochemical aspects of nucleophilic substitution reactions. In order to understand the stereochemical aspects of nucleophilic substitution reactions, we need to learn some basic stereochemical principles and notations such as optical activity, chirality, retention, inversion, racemization, etc. So, first is optical activity. Plane of plane polarized light produced by passing ordinary light through Nicol prism is rotated when it is passed through the solution of certain compounds. Such compounds are called optical active compounds. The angle by which the plane polarized light is rotated is measured by an instrument called polarimeter. If the compound rotates the plane of polarized light to the right, that is a clockwise direction, it is called dextrorotatory, Greek for right rotating, or the D from and is indicated by placing a positive sign before the degree of rotation. If the light is rotated towards left, anti-clockwise direction, the compound is said to be levorotatory, or the L form of a negative sign is placed before the degree of rotation. Such plus and minus isomers of a compound are called optical isomers, and the phenomenon is termed as optical isomerism. William Nicol, 1768 to 1851, developed the first prism that produced plane polarized light. Number 2, molecular asymmetry, chirality, and enantiomers. The observation of Louis Pasteur, 1848, that crystals of certain compounds exist in the form of mirror images laid the foundation of modern stereochemistry. He demonstrated that aqueous solution of both types of crystals showed optical rotation equal in magnitude for solution of equal concentration but opposite in direction. He believed that this difference in optical activity was associated with the three-dimensional arrangement of atoms in the molecules configurations of two types of crystals. Dutch scientist J. Van 't Hoff and French scientist Cille Bale in the same year 1874 independently argued that the spatial arrangement of four groups valencies around a central carbon is tetrahedral. And if all the substituents attached to that carbon are different, the mirror image of the molecule is not superimposed, overlapped on the molecule. Such a carbon is called a symmetric carbon or stereocenter. The resulting molecule would lack symmetry and is referred to as asymmetric molecule. The asymmetry of the molecule, along with non-superimpossibility of mirror images, is responsible for the optical activity in such organic compounds. Jacobs Hendrikus Van 't in 1852 to 1911 received the first Nobel Prize in Chemistry in 1901 for his work on solutions. The symmetry and asymmetry are also observed in many day-to-day objects. A sphere, a cone, a cube are all identical to their mirror images and can be superimposed. However, many objects are non-superimposable on their mirror images. For example, your left and right hand look similar, but if you put your left hand on your right hand by moving them in the same plane, they do not coincide. The objects which are non-superimposable on their mirror images, like a pair of hands, are said to be chiral, and this property is known as chirality. Chiral molecules are optically active, while the objects which are superimposable on their mirror images are called achiral. These molecules are optically inactive. Figure shows some common examples of chiral and achiral objects. The test given for molecular chirality can be applied to organic molecules by constructing models and its mirror images, or by drawing three-dimensional structures and attempting to superimpose them in our minds. There are other aids, however, that can assist us in recognizing chiral molecules. One such aid is the presence of a single asymmetric carbon atom. Let, let us consider two simple molecules, propane 2-ol. In figure, B is a mirror image of A. B is rotated by 180 and C is obtained. C is superimposable on A. And second is butane 2-ol. Figure E is a mirror image of D. E is rotated by 180 to get F, and F is non-superimposable on its mirror image D. And their mirror images, as you can see very clearly, propane 2-ol A does not contain an asymmetric carbon, as all the four groups attached to the tetrahedral carbon are not different. We rotate the mirror image B of the molecule by 180-degree. Structure C is obtained and try to overlap the structure C with the structure A. These structures completely overlap. Thus, propane 2-ol is an achiral molecule. Butane 2-ol has four different groups attached to the tetrahedral carbon and, as expected, is chiral. Some common examples of chiral molecules such as 2-chlorobutane, 2,3-dihydroxypropanol, bromochloroiodomethane, 2-bromopropanoic acid, etc. The stereoisomers related to each other as non-superimposable mirror images are called enantiomers. In figure, a chiral molecule and its mirror image A and B in figure B is mirror image of A. B is rotated by 180-degree and C is obtained. C is superimposable on A and D and E. In figure E is mirror image of D. E is rotated by 180-degree to get F, and F is non-superimposable on its mirror image D are enantiomers. Enantiomers possesses identical physical properties, namely melting point, boiling point, refractive index, etc. They only differ with respect to the rotation of plane polarized light. If one of the enantiomer is dextrorotatory, the other will be levorotatory. However, the sign of the optical rotation is not necessarily related to the absolute actual configuration of the molecule. A mixture containing two enantiomers in equal proportions will have zero optical rotation, as the rotation due to one isomer will be cancelled by the rotation due to the other isomer. Such a mixture is known as racemic mixture or racemic modification. A racemic mixture is represented by prefixing DL or plus minus before the name. For example, plus minus butane 2-ol. The process of conversion of enantiomer into a racemic mixture is known as racemization. Number 3. Retention. Retention of configuration is the reservation of the spatial arrangement of bonds to the asymmetric center during a chemical reaction or transformation. In general, if during a reaction no bond to the stereocenter is broken, the product will have the same general configuration of groups around the stereocenter as that of reactant. Such a reaction is said to proceed with retention of the configuration. Consider as an example the reaction that takes place when minus 2 methyl butane 1 ol is heated with concentrated hydrochloric acid. It is important to note that configuration at a symmetric center in the reactant and product is same, but the sign of optical rotation has changed in the product. This is so because two different compounds with same configuration at asymmetric center may have different optical rotation. On one may be dextrorotatory plus sign of optical rotation, while other may be levorotatory negative sign of optical rotation. Next is inversion, retention, and racemization. There are three outcomes for a reaction at an asymmetric carbon atom when a bond directly linked to an asymmetric carbon atom is broken. Consider the replacement of a group X by Y in the following reaction. If A is the only compound obtained, the process is called retention of configuration. Note that configuration has been rotated in A. If B is the only compound obtained, the process is called inversion of configuration. Configuration has been inverted in B if a 50:50 mixture of A and B is obtained, then the process is called racemization and the product is optically inactive as one isomer will rotate the plane polarized light in the direction opposite to another. Now let us have a fresh look at SN1 and SN2 mechanism by taking examples of optically active alkyl halides. In case of optically active alkyl halides, the product formed as a result of SN2 mechanism has the inverted configuration as compared to the reactant. This is because the nucleophile attaches itself on the side opposite to the one where the halogen atom is present. When -2 bromo octane is allowed to react with sodium hydroxide, plus octane 2-ol is formed with the OH group occupying the position opposite to what bromide had occupied. Thus, SN2 reaction of optically active halides are accompanied by inversion of configuration. In case of optically active alkyl halides, SN1 reactions are accompanied by racemization. Can you think of the reason why it happens? Actually, the carbocation formed in the slow step being sp2 hybridized is planar archiral. The attack of the nucleophile may be accomplished from either side of the plane of carbocation, resulting in a mixture of products, one having the same configuration, the OH attaching on the same position as halide ion, and the other having opposite configuration, the OH attaching on the side opposite to halide ion. This may be illustrated by hydrolysis of optically active 2-bromobutane, which results in the formation of plus minus butane to all. Students, through today's video, you have learned stereochemical aspects of nucleophilic substitution reactions. I hope you enjoyed the video. So, to keep receiving more videos from me, please like and subscribe to the channel and share it as widely as possible. That's all for now. See you in the next video.